Welcome back. The objectives of this video is to define sequences, we'll write terms of a sequence, and we'll find the apparent nth term of a sequence. Defining sequences. In mathematics, the sequence is used much the same as it is in ordinary English. Saying that a collection is listed in sequence means that it is ordered so that the sequence has a first member, a second member, a third member, and so forth. Mathematically, we can think of a sequence as a function whose domain is the set of positive integers. So instead of using function notation, we'll usually write using a subscript notation as shown below here. So our definition of a sequence is a function whose domain is a set of positive integers with values a sub 1, 2, 3, 4 to a sub n. Those are considered the terms of the sequence, and the domain of the function consists of the first n positive integers. This would be considered a finite sequence. We'll also look at infinite sequences later on. On occasion, you'll see 0 used as the first subscript. We've seen that in the past, actually. We saw that back in chapter 6 when finding roots. We used k sub 0, k sub 1, etc. when we substituted into our expression. Objective 2 is going to be to write the terms of a sequence. We're asked here to write the first 5 terms of a sequence given by this particular function. Our n, they must be positive integers, and we'll substitute values in for n and see what our outputs are. The first 5 terms of this sequence is as follows. Substituting 1 in for n and simplifying, we get -1. Then we substitute 2 in for n for a sub 2. Looks like we get 1/3. Substitute 3 in, simplify, we get -1/5, and so forth. Objective 3 is to find the nth term of a sequence. Simply listing the first few terms is not sufficient to define a unique sequence. The nth term must be given. Consider the following 2 sequences where the first 3 values are the same, 1/2, 1/4, and 1/8. But after that, it begins to take a turn. So these appear to be the same sequence, but they're not. They're different. So we'll be asked to write an expression for the apparent nth term of a particular sequence. So here we're given values 1, 3, 5, and 7. They're outputs of our sequence. We have to ask ourselves, what value of n is going to give us back a value of 1? What value of n plus 1, or our second input, is going to give us a value of 3? So when we input 2, we need to output 3. So we're thinking this might be 2 plus 1. In fact, we look at this sequence and we have, if n is 1, and we have 1, that's like n plus 0 equals 1. And then we have, to get 3, we put in 2 for n. We have n plus 1, n plus 2. Unfortunately, this is not a sequence because these values, what we're adding, is not the same. So this needs to be consistent. So this concept here doesn't seem to be working. When we take a fresh look at it, if we input 1 in for n and double it and subtract 1, we get 1 as our output. And then we put 2 in for n, double it, and subtract 1, we get 3 as our output. We put 3 in for n, double it, and subtract 1, so it looks like this pattern follows the pattern a sub n equals 2n minus 1. So there is a bit of trial and error here and number sense that we will find helpful. So here's another example. Write an expression for the apparent nth term of this particular sequence. So remember, our n's are going to be, 1, 2, 3, 4, and then we need outputs of 2, 5, 10. So these are somewhat ordered pairs, right? When you input 1, we output 2. When we input 2, we output 5. When we input 3, we output 10. So We have to figure out what's going on here. I tried squaring this. 1 squared plus 1 seems to work. That gives us to 2, and then square 2. Our n is 2, square it and add 1. That gets us to 5, square 3 and add 1. Sure enough, the apparent pattern here is n squared plus 1. So we can square our inputs, we can multiply them and then subtract. So there's lots of options here. So another sample, write an expression for the apparent nth term of a to the n for this particular sequence. So again, our outputs are 1, 5, 9, 13, and 17. Interestingly enough, they're always 4 apart. And we'll study that kind of change in a future video. We have to impose something on 1 that gets 1 back to us. We have to impose something on 2 that gets us to 5. We have to impose something on 3 that gets us to 9. But we have to impose the same thing on those to make that happen. So a bit of trial and error here. I tried squaring some of those. I tried squaring 1 and imposing a value, adding or subtracting, and that didn't seem to work. And then you can try doubling it, right? 2 times 1 plus or minus something, or 2 times 2 plus or minus something, 2 times 3. So as we go through that system, we might try tripling n. 3 times 1 plus or minus something, 3 times 2, 3 times 3, and see what happens. This particular sequence, it looks like we have to go all the way to 4. 4 times 2 minus 3. 8 minus 3 is 5. I skipped 4 times 1. 4 times 1 minus 3 is 1. 4 times 3 minus 3. 12 minus 3 is 9. 4 times 4 minus 3, 13, and so forth. So that does seem to work for us, is from 4n minus 3. So that wraps up this particular introduction to sequences, and we'll get some more practice of this when I see you in class.